Welcome back to the Natural Language Processing Learn from Scratch lecture series. And till now, we have seen all of the different stages in the NLP pipeline. So we have seen in detail about each and every stage in the pipeline, and we even saw the implementation part in the in the different segments that are very much important. Fine. So all of these stages are fine. Now you know the concept, you know the implementation part, fine. But then in the industrial setup, you need to know where exactly all of this works together, and then how is it being implemented in the real industry setup. So that is where we are doing this. We will be looking into this particular case study, specifically an industrial case study, specifically for the company Uber. So Uber has this NLP system. We'll look into what it is, and then we'll have this whole briefing of the industrial case study. Fine. So I think till now we would have covered the whole health pipeline. Along with it, we even covered the four industrial strategies that are seen after deployment of a model. Fine. So now we'll be looking into the real life case study of Uber. So before that, I'll have a quick recap of what is this NLP pipeline, what did we see till now, and then we'll go for the main part. Okay, so we started off with data acquisition. It included even data augmentation part in our conceptual understanding, and then we had the implementation part as well. For data augmentation, we used NLP aug, and for data labeling the augmented new data, we used Snorkel, and even implemented the Snorkel. And then we have the text cleaning part. Here is where we segment the sentences from the paragraph of the whole string, and then we remove the stop words and then punctuation marks and then digits sometimes, or even normalize the digits or normalize the Unicode. And we did a lot of these kind of tasks. And then we went to the pre-processing. Pre-processing is where we did stemming, lemmatization, and then tokenization. And then we even did advanced pre-processing, that is the POS tagging and NER, right? And then we saw the feature engineering, and in feature engineering we specifically saw two different pipelines, feature engineering for different pipelines. One was for the classical NLP pipeline, and the other was for the deep learning pipeline. So in the classical NLP pipeline, we use heuristic based rules, or we even use handcrafted methods to numericalize the text or the document or any the the subject or the main data that we are trying to make the NLP system understand and numericalizing it. So that was for the classical NLP. So we do it with different ways. In classical NLP, we come up with the handcrafted function. In the case of deep learning, we use word embeddings. We come up with the concept of word embeddings. We'll look into word embeddings in detail in the next lecture, which is where we'll see different types of text representation. Right. So that would be a separate lecture. There are a lot of different ways we can actually represent text. But in the deep learning part, we just saw the word embeddings. We use some neural network based libraries like the word to vec, glove, doc to vec kind of libraries for converting text into numerical form, and then input these numerical numbers directly into the neural network. In the case of deep learning based NLP pipeline. And then we went for modeling. And we saw how we start off with heuristics. And then if the heuristics are performing well, if it is performing well for the particular task, then we depend upon the heuristic itself directly. That was what we saw. And then we went and saw even how we can use heuristic based features as an input for models, for ML models. And then we saw how even the modeling can be done, and then after that we can actually do reapply heuristics for the output of the model, because sometimes the model might give us a controversial output, fine, or error based output. So for the in that case we reapply heuristics, and then we get the output, we display the output to the user. I'm saying all of this in the production environment, because in the normal case study we won't be reapplying heuristics, but then for the production environment, real-time users will be having, so our output should be perfectly aligning with the users principles or their viewpoint, so that the company or the solution providers don't get into trouble. So that is we reapply the heuristics. So the ChatGPT based output and the Gemini's output could be an example. The initial days of Gemini 1.0 or that one 1.5, Gemini 1.5. In that case, there were a lot of issues with the model, right? So they rectified it. How did they do it? They added heuristic based rules on top of this model's output, so that to prevent the output being displayed, controversial output being displayed, or text generated controversial text being displayed to the user. So this was one thing. And then we have evaluation. So in evaluation, we saw two different types, extrinsic and intrinsic. Extrinsic evaluation is done by the stakeholders or the client, and it mainly tries to check whether a particular business goal is achieved or not. That is extrinsic evaluation. In intrinsic evaluation is done by the developing team itself, AI developing team itself, and it is mostly of how well the model is performing for a particular task. And we saw all of the different metrics used there, starting with accuracy, precision, recall, F1 score, and then roof. Actually, it's ruse. In my previous video I called it as rouge or something, but then it's actually ruse. So ruse, and then blue, and then perplexity, and then MAPE, mean absolute percentage error, and then mean reciprocal rank, and then root mean squared error. All of these different metrics we saw along with their formulas. And then in the deployment phase, we saw how deployment happens, what all features need to be considered, how does it take place. So that kind of things we saw in deployment. And then we saw what is monitoring and then what is model updation. So in this whole pipeline, okay, we saw all of this in the production level. There is another thing, there is another part here, improving the model in between the developing thing itself. So I told you about the intrinsic evaluation, right? After intrinsic evaluation, if the model is not performing good, we can even use hyperparameter tuning and many other model optimization techniques. So that will be coming in this particular phase, improving the model phase. It'll be like done within the developing team itself. Fine. And then we saw the four different industrial scenarios or case study, or what is it, scenarios, for which we had come up with some decision paths or strategies to resolve those scenarios. The challenges posed by the scenarios. Fine. So this was the whole thing that we saw till now. Fine. Now we look into the whole whole new industrial case studies where we can see how all of these different things comes into play in the real world. Fine. So yes, we'll be looking into the customer support. So this particular NLP system of Uber is specifically for addressing a particular issue that Uber faced in its customer support team. Fine. So Uber operates in 400 plus cities worldwide. So based on the number of people, I think I hope you already know about Uber. Uber is a company that provides application for taxing, for booking rides for your taxis and availing all of these last mile transportation, commercial transportation. Fine. So that is Uber's short business objective. Fine. So they operate around in 400 plus cities around the world. So the number of people who use Uber every single day is huge. So you can actually properly understand why they have a lot of they receive a lot of these tickets. What are these tickets? Tickets are the complaints or the issues that are faced by the customer that they raise during an operation or some other issue. Okay, they could be something like the payment failure, or maybe the trip destination was not reached, or driver has done something. Also, that these kind of issues are addressed using these tickets. So we raise tickets, and then the customer support person views this ticket and then resolves it, calls you or texts you and resolves this particular issue for you. Okay, that is the customer support team. So on a day-to-day basis, Uber receives hundreds of thousands of tickets. Fine. So a customer support team, even if it is having a lot of people, like even say for 100 people in the customer support team, even then resolving this will not be, even if we say we have 1,000 customer support people, they'll have to have handle 100 tickets a day. That will be very much difficult. So how do they do this? So to do, it will take some time also, right? In resolving all of these customer issues, it's very much important that we resolve all of these issues with a limited time span or limited time duration. Otherwise, we would be, say for you, you yourself, as an example, like you yourself, when you're booking this particular Uber, and then you're facing some issue, the booking is not confirmed or something, and then immediately, if the issue is not resolved, you go for some other platform. You go for Ola or Rapido or something. Fine. So these are, that is why resolving this is actually a major task, and that is why they have come up with this LLP system. So to resolve all of these tickets and to mainly make sure the customer support team is able to really help the users, they made this kind of a system. So first, whenever a customer raises a ticket, he clicks on this help and then he gets this report an issue with this strip or fare review. All of these options will be there. If he clicks this, he'll get the following options. So what are the options? What type of issue do you have? This is what this user interface is asking the customer. So the customer will click on any of these issues, and then he'll get this, like, what was your tour parking fee? How much did you pay? Do you want to share any other additional details regarding this issue? And then you submit this issue. So this is an issue type hierarchy that they followed. And even then, even when you get this kind of tagging for this particular issue, customer support team had to go through all of this and then come up with the correct solution. So for each of these different issues, they will have some solution document, like a guide for them. Okay, for this kind of issue, follow these procedures. So they'll have this document. So the customer support team will have to see the issue of the customer and then say, okay, this is the issue. Okay, fine. Let me check it out. Okay, this is how we resolve it. Fine. Let me call him and then tell him this. So that is how they do this, right? So the customer support team will have to be very much quick in response for resolving the customer's complaint issues. So if we do this manually, it will be very much difficult. The support team will not be able to resolve or come up with the correct solution. They'll have to search for the solution. Okay, which page is the solution? Okay, what is the issue? Okay, this is the issue. Which page is the solution for this? So they'll have to search manually for it. If it is a printed document, that is why they had to come up with something. We'll see what they came up with. So support indirectly CS support agents face challenges due to variety of customer issue descriptions and thousands of possible issue types and resolutions. So as Uber scales, quickly identifying the issue type and correct resolution is crucial to reducing ticket handling time and improve user support efficiency. So that was, this description exactly says what I'm trying to convey you. I hope you understood. Fine. So we'll see what Uber came up with. Okay, so Uber has its own AI lab, though it's a business-oriented taxing company. It has even its R&D lab, and they introduced the Customer Obsession Ticket Assistant. It's an NLP system, and it works robustly for what? For this, resolve tickets faster and more accurately by using their models, and mainly it supports the customer agent, like customer support agent. So it actually recommends a particular solution document to the customer agent as per the issues type, or the ticket details of the customer. So the model would be here. I'll give you a picture based example of what this quota, how this quota works in a workflow. But then this is how they do this. But then I'll just give you a glimpse of what it is. So Quota enables quick and efficient issue resolution for more than 90% of our inbound support tickets. This was actually there in their this particular statement was there in their blog for Uber. They properly showed how 90% of their inbound support tickets are now efficiently, so issue resolution is taking place using this Quota platform. Fine, we call it as Quota, but yeah, customer obsession ticket assistant platform. So They have their own support platform as well. It's called as Machine Learning as a Service platform. It's called Michelangelo. That is what you're seeing here. Michelangelo. Michelangelo is their machine learning as a service platform that they have developed in-house for themselves. Fine. So on this platform, they deploy some machine learning models or NLP models, and using that, that is where Quota is actually being deployed. That is where Quota is actually being hosted. Fine. This platform is where the this particular assistant is being hosted there, and they use it in their whole framework of application for their customer support. Now we look into the workflow architecture of what happens. Really, where does this whole quota system works? So ignore the writings here. I'll just tell you with this picture itself directly. But then if you really want to go through the notes, you can actually go through all of these different description of the steps. So what happens? You given the whenever a new ticket comes in, it gets into the customer support providing portal. Fine, customer support platform, it provider or customer support platform. So it gets into the back end of the CSP, and then it gets into the model, the machine learning model, the NLP model, which the quota system has trained and kept. So this model will give out a score. How what score does it give? I'll tell you everything in detail. Just see where this particular whole quota system is working in the workflow, and then we'll go to the architecture or the whole main technical part. Now we'll see where exactly is the solution being used in the business aspect. Fine. So ticket is getting in. We have the quota system. We have the customer support platform backend, and the backend gives in the information about this ticket into the model. Model gives out a score. The score would be for the ticket and the solution document that they have for the particular issue. Fine. So this score would be given back again to the backend portal, and this will be saved in the Uber's data store. And now this will be repeated whenever there is a new ticket or some resolution is needed, or whenever there's an updation. This will be repeated, and then it goes on to the front end of the customer support platform, and this is where the customer support agent will be looking into these, and then it get the top three suggestions on solution. So for this particular ticket, what are the possible three solutions? Because for say on a day-to-day basis, the customer support team will be getting hundreds of thousands of tickets. They have different types of issues, right? So if you see, the Uber has 100 types of issues, 100 types of tickets. In the ticket issue itself, there are different several types: payment type of error, or payment type of ticket, or trip type of ticket, or some other type of ticket. So all of these are actually different types of issues or different types of ticket types, ticket issue types. So there are 100 issue types in the Uber's real life platform, and the solution documents that are there to address these different issues. There are thousands of solution documents. So imagine if you are a customer supporting agent, you'll have to see this issue ticket of the customer, and then go through thousands of the all of the each one of the thousand documents, and then from the thousand documents you have to pick up one and then say, okay, follow that, follow this, and then you have to instruct the customer. So it's very much difficult if he has to do it manually. That is why we are giving him some suggestions. We give some top three suggestions of from the thousand solution documents. So from these top three, the customer agent will pick as per the customer's need, and then he'll actually support the customer through call or through any medium of communication. Right. So this is exactly where the quota system, NLP system comes into play. So I hope now you understood what the whole workflow, how does the whole workflow works, like how is the whole workflow designed, and where exactly does this Uber's NLP system plays its part, right? This is where it plays its part. Okay. Now we'll look into the internal architecture of this whole machine learning model and all of this. How does this give the score? How does this work properly? Okay, before that, I'll give you what has happened due to this quota system. Quota reduces ticket resolution time by over 10% while maintaining or improving customer satisfaction, making Uber support faster and more effective. This is there in their blog properly. This is what they've observed after deploying this system in their whole application. Fine. So the resolution time was reduced by 10%. That is a huge number. And then they even improved the customer satisfaction. Customers were happy. Okay, I've done the whole resolution. The customer is supporting. Customers really thought of by the business is what the customers think after this kind of service. Too. Fine. So that was the whole thing. Now we'll look into the whole backend form. It's so much text, right? But then there are good representations afterwards. Just go through this. We'll now just go through what are the different attributes of this NLP2, right? What are the different uniqueness of this NLP2? So what it does primarily, it identifies the issue type and then recommends the best solution. That is what it does. Fine. What are the features that does it use? It uses the customer messages because the decade it takes in the decade, right? So the decade will have even the customer's message also about a particular issue. So that one and the customer's strip data and the issue hierarchy selections. And yeah, so where exactly? 200. Yeah, where exactly this particular issue, this ticket comes under? Which type of issue does this particular ticket comes under? So it'll see the issue hierarchy selections. So uses features from these, and then they did some feature importance of their model. Feature importance actually is an attribute for a model. You will understand which particular feature or in the data set, which particular feature or which particular column is very much important for predicting, for getting the score or for predicting a particular outcome. Right. So that with that they understood that customer messages are most important. So that is why they built the pipeline robust to multilingual text. We saw that, right? This was a challenge for the NLP system. So they have done this, like they have properly come up with the multilingual text-based NLP system so that customers can give any kind of language as an input. But then this particular model will be able to convert it into standard English form or some other form, and then use that input for predicting or coming up with proper outcome. Fine. And they chose word level analysis to capture text semantics. Fine. To truly understand the meanings of the customer's message, they did word level analysis. And then they used something called as topic modeling. It's actually a method that uses word frequency to infer meaning. Fine. So they count the number of words in a particular message or something, and then with the number of words or the frequency of that particular word with respect to that, they'll try to understand what type of document, what type of issue, or what type of text is given by the customer. Fine. So that is why it is used for inferring the meaning. Though this particular topic modeling ignores the word order, it is very much effective in classifying this particular issue type or this text of the customer and all of that. So that is what we're doing, right? We're trying to classify the issue type and then use that classified information for getting the correct solution document. So that is why document classification is very much here. The task is just document classification for information retrieval. For doing these two tasks is what we are primarily focusing on. These two tasks can be properly done with topic modeling, and that doesn't need the word order. It doesn't need that. That is why topic modeling was preferred here. Okay. So now we have the modern NLP. This was done in 2018. They published this particular work in 2018, and it is still working. Their production environment is still having this quota system in it. Fine. So this particular thing, whatever they've developed in house, they even improved it with deep learning models. So that doesn't require any explicit parsing or any of the pre-processing. I told you, right, for the deep learning based NLP pipelines, you don't need to do much pre-processing. You don't need to come up with a handcrafted function to pre-process your text. You can do direct word embedding, right, using a neural network, dense network again. So that was an advantage. Fine. Now we'll look into the internal architecture. So what happens? So we have the ticket info. The ticket info will be just or ticket ID or the ticket number, where is it from, all of those things, and then ticket text, whatever the customer has typed about this particular issue, and the trip data, which kind of trip as the customer uh, was involved in, and then we use all of this, and then for the text alone, for the all of the text alone, we tokenize it, we do some pre-processing, and then perform this latent sentence semantic indexing, and then term frequency, inverse document frequency, TF-IDF. We look into this in much more detail in the next lecture, that is in the topic of text representation. There are different types of text representation, I told you, right? TF-IDF is also one of the forms. So, but then I'll tell you what it is directly properly in the next lecture. But then for now, just understand this is one of the features that they took in. It is basically to numericalize the tokens. Fine. They use this for numericalizing, and this also for numericalizing, and then they use cosine similarity, and then they use point-wise ranking. This is specifically for retrieval, information retrieval kind of tasks. We use this kind of an algorithm, point-wise learn to rank algorithm. This is, and then we get the issue type and the solution. Bad. Fine. So this is how they have given, but then I'll give you in more detail. I have an architecture properly drawn after reading through their research work. So that will be very much detailed than this. Fine. So this is what I've drawn. So I'll tell you. Now we'll look into the pre-processing stage of this old pipeline. So we can see here. First, observe this diagram properly. So we have the solution documents. All of these documents are paired with their previously used tickets. So all of these tickets, whichever is present here, all of these are tickets which were previously used, like previously given by the customer. So that is where you're using the historical data. So what we said before, we'll be using topic modeling, right? So where the word order will not be taken into consideration. So we pair each and every, we take advantage of our historical data that we have already collected. So they have taken advantage of their historical data. So there is which is already paired with the solution documents. So for doing topic modeling, we get the text data or text input from each and every ticket, all of their features like the ticket information, ticket text, that is the text of the customer, and then the trip information. All of these different features are taken in as input, and those are actually pre-processed. So in the pre-processing stage, we collect these, and then we remove all of these are actually in HTML form, right? So they'll be in the HTML page form. So we have to remove the HTML tags. So HTML tags are removed. We tokenize the sentences, and they remove the stop words, lemmatize those words, and then we convert all of these text into bag of words representation for this particular document itself. Fine. So this is the bag of words representation. So what is this bag of words representation? I've already told this before, but then I'll tell you again. Bag of words representation, TF, IDF, term frequency, inverse document frequency, that term, and then the LSI, latent semantic indexing, and many other word embeddings like the word to vec, how they work. All of these are actually different text representation techniques. Text representation meaning numericalizing text numericalizing techniques. So we'll be having a separate video for briefing the details of how this representation or the conversion to this numerical form happens in each and every technique properly in detail. Fine. For now, just remember that they are using bag of words representation for transforming this or for making this text be understood by the model. Fine. So the numerical representation technique used here is bag of words representation. But then to give you a small glimpse of how this bag of representation works, imagine we have the whole word dictionary with you. Fine. So for using this, for example, you have 20 words in your word dictionary. That is your own dictionary. So you have 20 words in it. And you have a sentence one. So for each and every word in this dictionary, you will come up with the numerical representation for the sentence by saying that the sentence is represented by the numbers, and these numbers will be either 1 or 0, and it will be 1 or 0 depending upon if whether the same position in the list of dictionaries, if that dictionary word is present in the sentence, then it will be represented as 1. If the word in the dictionary is not in the sentence, then it will be represented as 0. So with that, for 20 words, you'll get a 20 element based a list of numbers 101010 something, depending upon the sentence for which you're transforming or making it into a numerical form. So are you understanding this? So a sentence will be transformed into a numerical or a bag of words. A bag of words in this document that will be converted into a list that would be converted into a list of numbers wherein the number should be 1 or 0, and it will be represented as 1 if the bag of words, whichever word is in that position, if that word is there in the dictionary, then it will be given as 1. If that word is not there in the dictionary, it will be given as 0. So it will be a combination of 1 and 0 that forms a whole list of numbers that represent this bag of word. So for each and every document, we collect all of these different words, and then we first process them, do all of this processing, and then convert them into a bag of words, and we represent them in the numerical format. Fine. So we do the same process for all of the documents. For each and every document, we do this. Fine. So this is the whole pre-processing as well as feature engineering process. So this involves even this is the feature engineering part, and the pre-processing part is this, removing the HTML and synchronizing and all of that. Well, we told you this. So this is the whole process. So before introducing the topic modeling procedure, we are doing this with the historical data. Now we'll move forward with topic modeling. So here what happens, we already have the bag of words representation for each and every document, and all of these bag of words representation will be used by the algorithms TF-IDF, that is a term frequency, inverse document frequency uh, metric, and even the latent semantic indexing metric. And with using this, we'll get the other important feature, and that forms the topic vector. So what are we doing? We just collected all of the bag of words for from the decades, already used decades, previous decades, for each and every document. We get the bag of word representation, and then transform these using the TF, IDF, and LSI into topic vectors, capital T1 or capital TJ. Fine. So this would be your topic vector. Fine. So this would be a topic modeling. So what is this TF-IDF and LSI? The TF-IDF uses the frequency. So the number of times a word is, or a particular word in this bag of word is there in this document, or this particular each and every document. So depending on that, we'll get a particular vector representation, and that vector representation is the topic vector. Fine. So you can see it for each solution, they create this. So here, this is actually a pictorial representation of bag of words for each and every document. Fine. From here, you get to topic modeling. Understood? So, yes. So we get the topic vector now. Okay, that is done. Next is feature engineering on top of this. Feature engineering is for the model itself, the main model which we'll be using. I will go to that later, but first we'll see this. So here, what we're doing, this is another type of feature engineering process. So here, we already have the topic vector for each and every documents. For each and every solution document, we have a topic vector now, using the bag of words representation and then the term frequency kind of feature representation. We get the topic vector for this particular document, for first document. Now, whenever a new ticket is given into the whole NLP system, the cosine similarity between the topic vectors, each topic vector and the new ticket would be giving us the cosine similarity vector. It could be if the topic vector is Tj and the new ticket given in is Ti, small ti, then the cosine similarity based vector which we get would be Sij. But then what is this cosine similarity? You will have the doubt, right? So here it is. I told you vector can be represented in a graphical way like this, right? So imagine this is your solution vector or the topic vector. Fine. For a particular solution, whatever topic vector you get, this is this. This is that vector. Let me just write it down here. So this is your TJ. I'm just giving you an example here. So it's not TJ, it will be TI or something. TI, yes, here in this case it is TI. And this is your TJ. And the closeness of this new ticket with this solutions topic vector would be your cosine similarity based Sij. And this is what will be given in as input. So this is actually feature engineering. We're selecting this feature to be one of the features that will be given inside the classification model. Fine. So this is the whole understanding here. So instead of giving, one could usually what happens is we can directly give. Usually what happens, we can directly give this topic vectors into the classification model. But then we are not doing that because the topic vectors might have, since it is out of bag of words for all the tickets, the number of words would be very much high. And even after transforming using TF IDF, this vectors dimensionality, the number of ordered pairs or number of parameters in that vector would be very much high. So it is high dimensional vector here, topic vector. That is why we are not using this. Anything that is higher dimensional will be costing us computationally, right? So we are just getting the similarity of this bigger topic vector with a new text based vector, and then with that we get the similarity vector, similarity vector. It's called as cosine similarity vector. That is Sij here. Okay. So this is the whole feature engineering that is done for the main classification task. Fine. So this is the main reason why we are doing this. It's already given you. Hi. While topic vectors can be used directly for issue classification and solution selection, their higher dimensionality and sparsity make training difficult. Instead, we apply topic modeling indirectly by computing cosine similarity. So you get the cosine similarity and then use that as an input. We'll see where is this going in. We'll see. This is just a part of the whole architecture giving this. Now what happens? It's given here again. See, they mainly compute the cosine similarity Sij between the capital T topic vector and the new ticket text vector, reducing the feature space from hundreds of dimensions to a few, making the model more efficient and scalable. Yes. So now we'll see where exactly this goes. Okay, I'll come to this point wise ranking algorithm, but before that, just see this. So we are giving in the similarity vector, that is cosine similarity, output of cosine similarity to the classification model. So here is where our actual modeling is taking place. All of these cosine similarity based outputs would be just our one of the features. Along with the similarity vector, will have a ticket features for this new ticket, whichever features it had. All of these text features and the trip, whatever trip the customers were actually involved with, that those trip features also will be given in along with the that is related to the new ticket. So ticket features and the trip features along with the new tickets and topics similarity vector would be given in as the input, and with that you will get the score. And this score usually for a classification model would be a probability, right? For any classification model. That is why I told you just learn the machine learning concept and then only then come to NLP. So I hope you know what is the how a classification model works, or at least what the output of classification model will look like. If you don't know it, I'll just give you a glimpse for it. So we have class 1, class 2, and class 3. So there are three classes we are seeing a classification problem, and the model each and every time will give us a probability of how much is it belonging to this particular class by chance. Fine. 0. 0.8, 0. 0.1, 0.1. So in this case, since the probability is 80% here, the model, we can actually conclude that this particular input is belonging to the first class. Fine. So this is the understanding of how our classification model works. I hope this makes sense. So usually this is the procedure. This is how classification model works. But here in this case, we're using something called as point-wise ranking algorithm. So how is this different from a normal classification model? I'll give you the example properly. So take this. This is actually a generic point ranking algorithms, like architecture or a design. So this particular algorithm is mainly used for searching, like for information retrieval. For information retrieval, we use this particular algorithm. So the concept is very much straightforward, man. We have a model, we take in the document something, and then we have the query of the user. Fine. With respect to the closeness between the query and the document, we give out a score, and with that score we can actually rank the particular document and then say, okay, this document is closer to the user's query and this document would be recommended. So this is the whole positive point wise ranking algorithm in general. But then it has one more parametric feature. Here, in this classification output, we get all the probability in the form of in number form, right? In point number or decimal form, which would be between 0 and 1. So it'll be a fraction or a decimal between 0 and 1. It could be 1, 0.5, 0.25, 0.23, something. So it'll be a decimal between 0 and 1. That will be the output of any classification model, like the probability of any classification model for a particular class. Fine. But then in this case, we train the whole algorithm in such a way that the output or the actual class predicted would be given as 1 whenever it is matching. So using a point-based learning to rank method, correct solution ticket pairs are labeled as 1 and sampled mismatches as 0. So this particular classification model takes in similarity between the two new ticket and the topic vector and these ticket features and trip features, right? And give out a probability. What we'll do is, if the probability is high, then we'll say that the solution ticket are matching properly. If they're matching correctly, then we'll label that as 1. So it'll become almost like a binary classification kind of a task. That is the main advantage of using point ranking algorithm. But then it has some disadvantages as well. But then in this particular case, since we are using similarity score itself, that is where this is working out. Fine. So whenever there's a perfect match or the probability is high, we consider that label as 1. If it is mismatching, if it is not giving a proper probability, if it is lesser than 0.5 or if it is lesser than the maximum 1, then it will be considered as mismatched and will be given as 0. This would be the scoring for this. Fine. So I've told you already. So this is what it's described here. We have used solution selection to explain Coda's ML approach. Fine. The cosine similarity, the ticket and trip features are combined to match tickets with over 1,000 possible. I told you 1,000 possible documents are here. For all the so for all the 1,000 possible documents, we'll have 1,000 topic vectors. So we have 1,000 topic vectors, and for each topic vector, we have to get the cosine similarity with the new ticket. For whatever new ticket comes out, a customer raises, for that new ticket, we'll have 1,000 different cosine similarity vectors here. All of these different cosine similarity vectors will be given is as an input independently, meaning at one time, one of the similarity vector, one of the topics, one of the solutions similarity vector, along with the trip features and the ticket features, will be given in as a input for the classification model. So one similarity score or similarity cosine similarity vector at one computation, at one epoch or something. And we'll do that same scoring for each and every topic vector or similarity score independently. So this would be one score. Again, we'll do the same process for the same new ticket with other topic vector. That will be another score. So all of these scores will be independently calculated, and then we'll compare the score, and then whichever score is higher, we'll give that as 1, and other scores which are smaller, we'll give that as 0. And the one given as higher score would be considered, and those would become your uh, top recommended solution, and that document would be recommended. That would be having the highest score. Fine. So this is the whole process. So the bag of words representation is transformed using the TF, IDF, and LSI kind of metrics to make it into a topic vector. The topic vector and the new tickets vector form is compared using cosine similarity, and then we get the cosine similarity score in terms of vector, and then that's vector would be used as an input for ticket along with the ticket features and trip features independently for each and every topic, for each and every document. And for each and every document, there'll be a separate score. And whichever document has the highest score, that document will be labeled as one. That document and ticket pair will be labeled as one, and the others will be labeled as zero. With that, you get the topmost possible good um, solution document recommended. Fine. So in this classification model, you can actually use any classification model. Here in this particular segment, they've used random forest classifier to score the pairs and then get us the proper top three ranked solutions so that you can suggest it to the support agents. So this is the whole point wise ranking, learn to ranking algorithm. It's actually a learn to rank algorithm. In that we have several types of different algorithms. Here it is the point wise ranking algorithm. Fine. All of these algorithms are actually used for search engines. This learn to rank algorithm itself is mainly for search engines. Fine. So, but then we use it here for getting the perfect document. So I hope it is clear now. You understood how we get the cosine similarity vector, and then of between the topic vector and the actual new tickets vector. This you might ask me how did we get this TI small TI, right? So TJ. We'll again do the same pre-processing techniques and then convert this new ticket into a numerical form, and then compare that numerical form with this topic vector's numerical form, and then get a cosine similarity. And this cosine similarity based numerical form would be used as input for the classification model. So that is the whole process. And then even after classification, whatever score we are getting for each and every document, will get a score. And whichever document and new ticket pair has the highest score, further will give label as one, others will be zero. So that is straightforward. Fine. So overall, this is the whole architecture. So we use the historical data. Using the historical data, we get the previous tickets which already led to the document one, and each and every different document. As per the text input in the ticket, previous ticket that is used for a particular document, we get the bag of words representation for that particular document. And then we use this bag of words representation to get the term frequency and inverse document frequency metrics and the latent semantic indexing metrics. Using these, we'll get the topic vector. And for each and every document, there'll be some topic vector. So that if there are m solution documents, here in this case, we have 1,000 solution documents. So there'll be 1,000 topic vectors. Each and every topic vector will be compared to the new tickets vector form or numerical form using cosine similarity algorithm, and we'll get the similarity vector representation of how similar these two things are. Two vectors are topic vector and the new ticket vector, and we'll get 1,000 of these because this one new ticket will be compared with 1,000 topics, and we'll get 1,000 of these different cosine similarity vectors, and each of the 1,000 similarity vector would be given individually every time with the ticket features and the trip features in the classification model, and we'll get 1,000 scores for one ticket. We'll get 1,000 scores, and out of those scores, whichever is highest will be labeling it as one, remaining would be labeled as zero, and that whichever is labeled as one will be alone saved in the data store. Like this will be the score, right? What did I tell you in the workflow? In the workflow, I told you this score would be again given out here and will be stored in the data store, right? Uber data store. So the score will be, we'll get the score and then will be stored in the Uber data store. So this is the whole architecture. I hope you understood it properly. It's very much simple, right? If you actually, for seeing it, looks like almost many steps are involved. But then if you really go through it in depth, in detail, it's very much straightforward and simple. So that's the beauty. Fine. So we got the whole overall architecture of this real-time industrial use case. Fine. So what has been the impact of this, or what has been the performance of this quota system? We'll see. You might ask me, why did we go for this point-wise labeling? We could just go for this direct score itself, right? Why do you have to again make a labeling of this score? We have 1,000 scores. We can directly use this 1,000 scores and get the. We can directly store all of these 1,000 scores, right? Or we can just store the score which has the highest in this 1,000 scores. That alone will be stored. Like for example, we have 1,000 scores for each and every new ticket. What we can do, we can just take the highest score having pair. So whichever document and new ticket has the highest score, that alone will be taken in, and that can be stored, and no need of going for labeling and not labeling and all, right, one and zero. But then they did that experiment, and they got to know that whenever you do point-wise ranking kind of algorithm, kind of procedure, whenever you label the highest score as one and the remaining things as zero, you save the part which is one alone, right? And that one is saved in this data store. Since it is having higher labeled data, again, when you are training it, it is becoming easier for them, and then the performance of the whole system is increased than going for just multi-class classification. So cosine similarity based point-wise ranking algorithm outperforms the multi-class classification algorithm with direct topic vectors. And even they did this process. They didn't just do it with point-wise as the ranking. They directly added the topic vectors. So we had this doubt, right? Why should we go for cosine similarity? We can directly get this inside the classification model and then compare it with the new ticket. Why are we even going for this cosine similarity? You might ask me. This is the main reason. By adding just this cosine similarity along with this point-wise ranking, they were able to increase the accuracy by 25%. Even with the same parameters, all these two things, they did it with the same classification model. That is the random forest here, with the same parameters and same data set. But then with point-wise ranking and the cosine similarity based input or feature engineering, they were able to increase the accuracy by 25%. That is a huge improvement in the performance. So that is a lot. That is why this was selected as the best one for our whole Coda system, or the customer obsession tech, technical assistant. So that one was done, but then now they compared which classification model itself can we go forward with. Here they experimented with random forest, but then they wanted to come up with something better. So with time, so they have to become better, right, with time. So they tried doing it, they improved it, and then they experimented with the deep learning models for classification, and they saw clearly that deep learning models are doing better than the random forest. So in the real time quota system at present, deep learning model is directly used in the same architecture like how I showed before. So this is the whole process. So we are using a deep learning based classification. We are using a deep learning based classification model, and then we are getting the score, and then this whole process actually taking place. This is the overall architecture now. Fine. So yes. So you might ask me, why did we even do this? But then see here, we you might not ask me, but then what is the real quantifiable impact? If you see the quantifiable impact here, it's tens of millions of dollars. They have saved tens of millions of dollars because of this quota system's ability. Mainly its ability to resolve the tickets fast at a faster and more accurate way. Fine. So this is the impact. So with that, we wrap up this whole industrial use case of Uber. I hope you got an understanding, and you come to an understanding of appreciating the whole aspect of NLP here. So we solved a real life world problem using a proper robust NLP solution. Fine. So this is the best industrial use case that I could get on and then present it to you to make you understand and appreciate the whole NLP systems pipeline, and how all of these different phases of pipeline work with each other, how they integrate with the whole workflow system and the whole application of real-time software. Fine. So I hope this made sense and it's useful to you. So in the next lecture, We'll look into the different text representations for converting the text into numerical forms. So there are different, I told you already, right? There are different techniques for converting text into numerical forms. So we'll look into all different types of numerical representations of text in detail in the coming next video, in the next lecture. Fine. So until then, we'll see you. But then continue practicing the NLP modules, complete each and every video properly from the start till the end. Make sure that you're disciplined, make sure that you're consistent, make sure you revise and experiment with the topic that I teach you on. Fine. So, yes, we'll see you in the next lecture.